Okay, hello. Okay, now can everyone hear me? Good, okay. Okay, that's good. Hope everybody's having a good week. Um, Judging by the chat window, I can't tell actually if that's sports or video games. Okay. Yes, I guess sports makes no sense. It would have to be memory of sports. Okay, so anyway, let's start with um, today. Actually, we're going to go on to we're going to do one more graph sketching example, and then we're finally going to go on to the next section. The last section we're going to do in chapter 4 is 4.7. We used to do 4.8, but we're not going to do that anymore. And as I think I've announced before, 4.7 is the last section you're responsible for on the next midterm. Of course, we're going to do chapter 5 for the final. So I just want to finish up 4.6 with another graph sketching example, and then we will do, and then we'll go on to applied optimization. Question: when is the midterm? The midterm is going to be on. Midterm is going to be on. Well, it's going to be a 24-hour window on Wednesday, April 22nd. So I believe we're going to start that at noon on Wednesday, April 22nd. You will have 24 hours until noon on Thursday, April 23rd, to start the test, and it'll give you, I think, 90 minutes. So yeah, so it's once you open it up, it's timed. It's like the quizzes. We've actually been doing those to try to train everybody for this mode of taking a test. Question: what lesson does the midterm start on? That's Leo's question. It's going to start at 3.2. So the last thing we did for the previous midterm was 3.1. 3.2 is the beginning of the derivative rules. You've already taken a quiz on the derivative rules themselves, so you wouldn't expect to see something that's just find the derivatives of a particular function, but you might have to do it as part of other problems like L'Hopital's rule, like optimization, like finding critical numbers. So you'll have to be able to use those rules, but except for logarithmic differentiation, which wasn't on the derivatives quiz, you might see a problem that's specifically about that. So, okay. Will you need to upload stuff from like the quiz from Tuesday? Our current thinking, as we talk about how to design this exam, is probably no. It turns out most people were doing that quite correctly, but there was another class where it didn't go so well. So I think we're thinking of maybe simplifying it by not doing that. There is a format of Canvas question where we can ask you to type a response, like we can ask you to explain something. And so rather than have you write something on a piece of paper like math, we might ask you to explain some principle as part of a question and grade you on how well you do that. So you can expect to see something other than just check the correct box or fill in a box. But I'm thinking we will probably not do the upload of pages, just because it's kind of nerve wracking. Because if I tell you to spend half an hour, if I tell you to spend 15 minutes and then spend the rest of the 15 minutes uploading, some people will try to sneak in like some extra time on the exam and then run out of time to upload, and it's kind of stressful. Okay. So let's see. Somebody asks, is it all multiple choice? The answer is no. It would use the various formats of Canvas. You're gonna if you took the quiz this week, you saw another one of those, another type of question that Canvas can administer. So, okay. I'm just waiting for the question, then we'll get started with today's infamous humanizing activity. Okay. Let me. Okay. So this can be considered part of the series of walking through parks with the professor. So I found another park today. Not today, actually, last week. This one was not as close to my house, but I was biking. I'm not sure exactly how far you're allowed to go from your house. This was probably 7 or 8 miles away. I believe if you're exercising, you're allowed to be out as long as you don't get within 6 feet of anybody. So don't tell anybody. Anyway, I came across this park, and it had this kind of this sort of shed with a police vehicle in it, and I thought, well, what is that? They keep their police vehicle in this nice glass shed. So it turns out when you look a little bit closer, it's actually a smashed up police vehicle, and when you look even a little bit closer, it's Port Authority of New York and New Jersey police vehicle, and it's got a little monument explaining that this is actually a park dedicated to the people who died in 9/11, or at least some of those people. And this is actually a piece of this brown object is actually a piece of the beams from the World Trade Center. So, anyway, the what occurred to me as I was looking at this, it's not really my thing to go look at memorials exactly. Oh, where is this park? It's in Mercer County, New Jersey. It's in Hopewell, actually. Anyway, it occurred to me is just in the interest of keeping a little perspective on things that are going on, I thought to catalog the various different crises or disasters that I've actually lived through, and as a way of reminding myself we will all get through this. So I thought I'd share that list with you. It's kind of a top 10 list. So crises or disasters I've lived through. There is the Cold War, or at least the end of it. I was sort of born at the sort of the tail end of the Cold War. It was Watergate, 1972 to 74. That was the original Gate crisis. That's now everything gets named Gate, it seems. There was the seizure of the American embassy and hostages for 444 days. That was in 1979 to 1981. Chernobyl, 1986. The Loma Prieta earthquake, 1989. The Florida recount in 2000. And interestingly, if you notice, there are no events in 1990. The columnist George Will actually referred to the 1990s as, quote, our holiday from history. It seems that almost nothing bad happened in the 1990s. So and there was 9/11, of course, in 2001. The SARS epidemic in 2003. You can actually, the SARS was actually caused by a different coronavirus that's related to the current one. So you can actually think of that as like coronavirus, the prequel. It's kind of like the coronavirus is Better Call Saul to the current virus is Breaking Bad. And of course, the financial meltdown of 2007 through 8, and the swine flu epidemic of 2009. So there are. So anyway, it comes out to about one crisis every 5 years on average. So we will probably good one, cats, yeah. So all right, I'm glad that actually went over, because yesterday's class, one of the items on the list was the 2016 election, but I've heard there were actually people who thought that was correctly decided. I've never met any of them, but I decided to leave that one off the list. So anyway, the let's see. So anyway, it's very possible that, one day you could be walking through the park in 20 years and find a different type of memorial, such as this, memorial to a previous disaster. You might think, by the way, that that's the coronavirus, but actually that's the Canvas symbol. You can remember that horrible spring when your Canvas classes got moved to Canvas. So, okay. I'm just enjoying reading the comments here. Let's start it. Okay. Oops. Yeah. Okay. So I just wanted to go back to a question. I think it was Leah who asked, does this mean we won't be able to get partial credit on the exam? In general, it is true that partial credit is going to be kind of limited because of the format of the exam. There will still be some opportunity to get partial credit based on the explanations that I ask you for. That's part of why I would do that. I don't want to commit to that because we're still in the this is all new for us. We haven't written the exam yet. We're still trying to learn from other departments and figure out the best way to do this. But if I were to ask you, let's say, something like I did the other day, like explain why something is a critical number, there would be opportunity for partial credit on that. And as you also saw on exam one, it's not as if multiple choice is the only type of question we can ask. We can ask, I can ask something like choose all that apply. Like if you recall, I asked questions like, which of these limits is equal to 2/7. So you can get partial credit for identifying some of them and lose partial credit for not identifying others. So it would be that kind of exam. So yeah, for example, I see somebody in the comment is, I'm glad you think we're doing it right. We still have yet to run an exam, so I don't want to be too haughty about other departments. But one thing we've learned is that things like Proctor Track, don't really work very well, or at least they're not really set up. We're not really set up to use them and just adopt some untested technology in this type. So I don't think we're not gonna do something like that. Anyway, let me get on to where is there we go. Here we go. Okay. Start class. Okay. So let's get back to math while I actually turn the laptop over. Okay. So what we've seen the other day is that we can sort of sketch a graph based on derivatives, because derivatives have a certain derivatives give the shape of a graph a certain look. So we saw, for example, that if we have a graph that looks like this, we're able to say that its first derivative is positive and its second derivative is also positive. That's because this graph is not only increasing, but is also concave up. And then at the same time, we could have a graph that's increasing but concave down, and we would be able to detect that because the first derivative would be greater than 0 and the second derivative would be less than 0. Recall that the first derivative tells us the monotonicity of the graph, tells us whether the graph is increasing or decreasing. The second derivative tells us its concavity, whether it's concave up or concave down. So we'd have here, this is going to be, first derivative is negative, indicating it's decreasing. The second derivative is concave up. And then here we have a graph that is decreasing and concave down. And it can also determine things based on the mins and maxes. So for example, if I know that this point, suppose that this is point C, if I can say that f prime of C, put it in, C equals 0 and f double prime of C, sorry, is less than 0, then what that tells me is that this must be a max. And that tells me a couple of other things about what's going on in the intervals around the point, because if it's a max, this is what I'm doing here, by the way I've written this out, is this would detect that this is a max by the second derivative test. I discovered that, based on this fact that that point is a critical number, based on this fact that the graph is, concave down, that would tell me that the shape of the graph is like this. But from that, I can also infer that since it's a max, it must have been increasing there and decreasing there. So that tells me also that f prime of x is greater than 0 to the left, and f prime of x is less than 0 to the right. So I can infer various things, from these patterns. So from that, we can sketch a graph. So that's what we're going to do today. We're going to sketch sort of a more complicated graph than the one we did the other day. So example of graph sketching. Okay. So what we're going to do is we're going to sketch the graph of this. Oh, let me just turn off the camera because we don't need that much as you guys would like to see me. Okay. So we're going to sketch the graph of this function. F of x is equal to x squared over x squared minus 1. And I've given you the first and second derivatives of the function. Just like I said, it's just kind of easier for me to do that than that way nobody gets the derivatives wrong, and it becomes a question of how you interpret the derivatives. So the first derivative is negative 2x over x squared minus 1 squared, and the second derivative is 6x squared plus 2 over x squared minus 1 cubed. So as I mentioned before, to do these problems, you need lots and lots and lots of workspace. So I've left myself a couple of sheets of paper to do this. So let us do this. All right, so the first step, as you might recall, was to find the first and second derivatives, but those are given. Okay, next step is to find transition points. Anyone recall from the other day what transition points are? Ooh, okay, so got a little bit of confusion about this. So transition points are places where either f prime of x equals 0, or f prime of x does not exist, or f double prime of x equals 0, or f double prime of x does not exist. And these, of course, we called critical numbers, but we're looking for another type. We're looking for sort of a broader category of points. In other words, not only places where the first derivative is 0 or non-existent, but the second derivative. We're talking about transitions in the shape of the graph. In other words, places where it might change from increasing to decreasing, or concave up or to concave down. So that's, or even both. So we're looking for a broader class of points. An inflection point is certainly is only going to occur at a transition point, but not every transition point is an inflection point. So anyway, we have here, what was I going to say? Okay, so we're going to look for the transition points, which we're first going to do by looking for critical numbers. So let's recall that f prime of x, actually, let me just copy I'm just going to copy the functions from the other page so we have them here. Okay, so make that a little smaller so it doesn't take up too much space. Okay, so we have the definitions of the function and its derivative. So what we're looking for is where f prime of x equals 0 or f prime of x does not exist. So first of all, f prime of x equals 0 when x equals 0, right? Because f prime of x is negative 2x over x squared minus 1. If we put a 0 in the numerator, we get a non-zero, then we get 0 minus 1 squared, or 1. In the denominator, we've got 0 over 1, which is 0. Now, next question is, what about x equals plus and minus 1? Are these transition points or not? Or actually, are they critical numbers or not? Let's ask that. What do you think? Okay, so we've got some yeses, based presumably on the fact that x squared minus 1 squared is in the denominator. If I square either plus or minus 1, I get 1, so I'm going to get 0 in the denominator. It is true the derivative is undefined at that point. However, if you notice, for the very same reason, f itself is undefined at that point. Number can't be a critical number of a function if the function isn't even defined at that point. So a little bit of subtlety in the definition. It's not enough just to look for values of x where the derivative is 0 or undefined, but those have to actually be in the domain of the function. Which is not to say that we don't care about plus and minus 1, because there's definitely something going on with the function at plus and minus 1. It's just that we don't technically call them transition points. So, okay, so let's okay, so we can say is that x equals 0 is a critical number. Plus and minus 1 are not, but we'll keep them in mind anyway. This is because when we get division by 0, as you know, if you have non-zero over 0, that tends to indicate, we learned in chapter 2, that tends to indicate that you have an infinite limit, which we interpreted as a vertical asymptote. So we'll do that formally a little bit later, but just, to cut to the chase, that's where the vertical asymptotes are going to be. So, all right, next thing we need to do is look at f prime prime of x equals 0. So when is 6x squared plus 2 over x squared minus 1 cubed equal to 0? The answer is f prime prime of x is never equal to 0, because there's no way to make the numerator of that 0. 6x squared is always going to be 0 or positive, so 6x squared plus 2 will always be a positive number. You're never going to get 0. Of course, we still get, plus and minus 1 will still give us a 0 in the denominator, so you get an undefined second derivative, but for the same reason that we just covered, that's not part of the domain of the function, so those are not going to be transition points. So we can conclude that the only transition point is x equals 0, but we will consider behavior across x equals plus or minus 1 because those are asymptotes. Okay. So when we start to draw the graph, you'll see what I mean by that. So, all right, so we found the points that we actually need to think about. So what it's useful to do here is to draw all the points you need to think about on a number line. What we have here is a transition point. We have a transition point in two places where f is undefined. So what we're going to do is pick points in between them as test points for the first and second derivatives. And the points I'm going to put in are -2. I'll continue writing these in red like I did the other day. So these red points are the places where I'm going to actually check the value of f and f prime to see what's going on. That's where we're going to see what the behavior, concave up, increasing, concave down, etc., is doing in this interval, this interval, this interval, and this interval. So recalling that once again, f prime of x equals -2x over x squared minus 1 squared, and f double prime of x equals 6x squared plus 2 over x squared minus 1. So from that, what we'll get is we're going to calculate all the red values. We're going to calculate the first and second derivatives. And what we get is f prime. I've done this in advance, obviously. F prime of -2 is 4/9. F prime of -1/2 is 16/9. F prime of 1/2 is -16/9. And f prime of 2 is -4/9. And put in double primes. F double prime of -2 is 26/27. F double prime of -1/2 is -224/27. F double prime of 1/2 is -224/27, and f double prime of 2 is 26/27. Okay. So from this, recall, we don't really care so much what the values of these functions are. What we care about is whether they're positive or negative, because that's what tells us whether the functions are increasing or decreasing on the particular intervals. So what we can conclude is that f is increasing on -∞ to 1. Put in the number line so you can see it a bit. And -1, 0. F is decreasing on 0, 1 and 1 infinity, f is concave down on -1, 0 and 1, 0. Sorry, 0, 1, I meant. And f is concave up on -infinity, -1, and 1 infinity. A little bit of subtlety, though, that I just want to point out when it comes to that third line. Technically, what I've done is I've been testing points in between transition points, but recall that 0 was a transition point because its first derivative was 0, not because its second derivative was 0. So it's possible that the interval of negative concavity actually includes 0. And in this case, it does. If you take a look at f double prime, if I plug in 0, what I get is 0 plus 2 in the numerator, and then I get 0 minus 1 cubed, or -1 in the denominator. So f double prime of 0 actually equals -2. So it's negative. So I can actually include 0 in the interval of concave down. In general, somebody asked how you know when you have to do this. The answer is, if the function is actually defined at a point that joins two intervals, you want to check that point to see if it's you want to check that point to see if it should be included in the interval of concavity. So I'm going to change this slightly and write this is -1 to 1. Okay, any questions? Okay. Oh, we can also observe, by the way, that because 0 is a critical number and f is concave down on that critical number, we can observe that f has a local max at x equals 0. That's the second derivative test. Okay. Let's just also look at the asymptotic behavior. Formally. So recall that f of x equals x squared over x squared minus 1. So we find the limit as x approaches infinity of x squared over x squared minus 1. I think many of you recall from chapter 2 that when you're taking a limit at infinity, you can just look at the coefficients of the highest powers if the two highest powers match. So that's just going to equal 1 over 1, or 1. And also the limit as x approaches negative infinity of x squared over x squared minus 1. I don't want to go over chapter 2 again, but just recall that this limit is also going to be 1 for the same reason. If you forget how to do this, you can actually solve this one by L'Hopital's rule. You could just take the derivative of the top and bottom twice, and you'd get the same limit that it's 1. So what we can conclude is that y equals 1 is a horizontal asymptote of f. And then we just need to validate our suspicion that x equals plus and minus 1, where we got division by 0, are actually vertical asymptotes. So the limit as x approaches 1 from the positive side of x squared over x squared minus 1 is, if you notice what this is going to be by substitution, is 1 over 0. So that's going to actually if I imagine plugging in a number a little bit more than 1, like say 1.1, I'm going to get a positive number in the denominator and a positive number in the numerator. So this is going to be plus infinity. And for the same reason, limit as x approaches -1 from the left, this is also going to be a 1/0 limit, where we imagine plugging in, say -1.1, we're going to get a positive number on top and a number slightly bigger than 0 on the bottom. So that's also going to be positive infinity. That's enough to declare that x equals 1 and x equals -1 are vertical asymptotes. Okay. So any questions about anything I've done up to this point? How did I know they were asymptotes at the beginning? Basically, from this fact, we learned way back when in chapter 2 that if you try to calculate a limit by substitution and you get something that's not 0 in the numerator and something that is 0 in the denominator, what you have is an infinite limit. So what that means is that I know that, as x approaches 1, I know that the function has to either approach that infinity or that infinity. So then I just have to try plugging in numbers on either side to reason out which one it is. But if I can find that, any of the 4 possible combinations are true, that either the right or left limit is positive or negative infinity, that's enough to declare that it's an asymptote. So I suspected it because substitution gave me 1/0. And then I just had to formally validate it in this step. Does that answer the question? Okay, good. So, all right, so let's go back to the drawing. All right, so here is where we're going to draw our graph. Okay, so what you want to do is we're going to put in all the points. There's 0, there's -1, there's 1. I'm going to put in the asymptotes that we found. And we found a horizontal asymptote as well. So I'm going to put in all the asymptotes. Okay. Julian, you got how I found the horizontal asymptote, right? Okay, good. So, because that was the definition, is if the limit of as x approaches either positive or negative infinity is equal to a number, then that number is the horizontal asymptote. So, okay, so now what we want to do is down here on the bottom, I want to write f prime and f double prime. I'm going to make sort of a chart here. Okay. And I just want to continue these lines downward. These are the intervals we're going to be considering. So what we know is that f prime was greater than 0 here, and it was greater than 0 here, and less than 0 here, and less than 0 there. That's from one of the other pages. I just don't want to flip back to it. And what we also know is that f double prime was greater than 0 here, less than 0 here, less than 0 here, and greater than 0 there. So what we have is the function is increasing here. it's decreasing, or sorry, it's increasing here. It's decreasing here and decreasing here based on its first derivative. We also know that it's concave up here. We determine that it's concave down on this entire interval from -1 to 1, and it's concave up here. And sort of redundantly, we can note that this point, because we have increasing to the left of 0, decreasing to the right of 0, and we also have concave down all the way through 0, we can observe that this point is a max. So going back to the definition of the function, if I plug in 0, what I get is, if I plug in x equals 0, I get 0 over 1, which is 0. So let's put in that as kind of an anchor. That's going to be 1 point on the graph, and we know that it's a max. And we also know that the function is from -1 to 0 is increasing and concave down, and from 0 to 1 it's decreasing and concave down. So we can kind of infer that the function looks sort of like that. And then what we have is, we know the function is, let's go to the right. To the right of 1, it's going to be decreasing and concave up. So it's decreasing and concave up and has an asymptote at x equals 1. We kind of know that it can't look like that, because that would be an example of approaching an asymptote, but that's increasing and concave down. So decreasing and concave up is going to have to look kind of like this. And to the left of -1, we have increasing and concave up, and it also approaches -1 as it also approaches +1 as an asymptote, and it's got to be concave up and increasing, so it's going to have that kind of shape. So there's the graph. Okay, so any questions about that? What's the hard? Oh, let me actually write these in. So y equals 1, x equals 1, x equals -1. Thank you, Zach. What is the horizontal asymptote, was the question Eric asked. So over here, I know I did it really quickly, but we got was that the limit as x approaches infinity is +1, and the limit as x approaches -infinity is also +1. So that means that x equals 1 is an asymptote. Sorry, I mean y equals 1 is a horizontal asymptote. How did you determine which side of the asymptote to draw it on? That's a good question. Basically, I inferred it from the other information. So we know that the function is increasing is decreasing and concave up. So focus on this, decreasing and concave up. If it's decreasing, it has to be coming from the top and going down as we go to the right. So that's what tells me that I'm starting from high up and going low. The fact that it's concave up on this entire interval is what's telling me that it has this shape. Let me just show you a slightly different shape, and you'll see what the problem is with that. So let's suppose that I had a function that looks like this. So here's also y equals 1 is a horizontal asymptote. But take a look at what happens. Look what I get here. I have 2 points that I then have to think about. Let's call this, I'll just put in 2 numbers, 1 and 2. This is now a min. And this now has to be an inflection point. In other words, you can see that the function looks concave up there, but in order to approach the asymptote from the bottom, it's got to be concave down. In the problem that I gave you, I didn't have that. Instead, what I had was I had that it was decreasing and concave up the entire time. So what that meant is that since it never changed, here we have decreasing and then we have increasing. It never changed from decreasing to increasing, and it kept its same concavity the whole time. I knew that it had to look like this. If I had a different situation where I still have a horizontal asymptote, I'd have, I would have had a different profile in the first and second derivatives. The answer is I based it on the combination of monotonicity and concavity. Go back to this picture. As you see, the combination of concavity and monotonicity gives us different shapes. The top two curves here, this one and this one, they're both increasing, but they have different shapes. What you can see is that the one on top looks like it's heading out toward infinity as we go to the right, whereas the one on the bottom is the one that actually looks like it could approach an asymptote if it had to. So that's what I'm basing it on. You should check for a horizontal asymptote. So sorry, Eric's question was, how do you know to check for a horizontal asymptote? If you recall the example that I did the other day, I actually did find the limit as x approaches infinity and negative infinity. It's just that what we found was that there were no asymptotes because that was a cubic function, and we found that it was a quartic function. So we found that it approached positive infinity to both the left and the right. So what I found for the infinite behavior was just that the functions went out, those two functions, that function went all the way to infinity on both sides, so it didn't have any asymptotes. So it would be normal to check the limits as x approaches infinity for every function as you do these. Okay. Step 2 again. Yeah, then I just want to go on to the next topic and we'll do that. So let's see. When you say step 2, you mean here? Okay, I think this was what the question was. I mean, essentially what you're doing at step 2 is you're finding the places where concavity or monotonicity, in other words, increase or decrease, might change. And those are only going to happen at places where the first or second derivative is either 0 or non-existent. So that's really what I'm doing here. When I discovered that x equals 0 was a transition point, what I did is I discovered it just by looking at where f prime and f double prime were 0, and I found the only place where either of those were true was at x equals 0. So that's step 2. Anyway, I actually do want to leave myself enough time for the next topic because I want to go on to applied optimization. So maybe I'll come back to that a little bit later or in future lecture. One of the things that's nice is we're actually a little bit ahead. So what that allows us to do is we're going to be able to review a lot of these concepts as they sink in more later. So, okay. So we get to a topic now called applied optimization. This is section 4.7. And to summarize what this is really all about is this is about taking a word problem and translating it into a find the min and max of a function type of problem. So this is really mostly about interpretation of word problems, but what we're then going to do is use the optimization procedure to find the minimum and maximum value of a function on an interval in order to solve the word problem. So the calculus you should already know from section 4.2 because we did that. The part that's that you have to practice, I find most people have to practice, is translating the word problems into the correct function. So we're going to go through a number of these. These really comes up in. This is probably one of the most important applications of calculus that you're going to use. Essentially, what this is saying is that calculus can tell you how to find the best and worst solution of any problem as long as you can write the problem down as a function. That's and this comes up over and over again in engineering, economics, science. So this is, if you ever use calculus beyond this class, this is probably where you're going to end up using it, is solving this type of problem. So the procedure to do this, I've just written it down here, and this is in the published notes as well. You want to identify the quantity to be optimized. So whatever that is, you want to find, the maximum volume of something. You want to find the minimum number of dollars that something can cost. That's what you're looking for in number one. We're going to do at least one problem involving finding volume or area, finding area after this slide, but it could be anything. So next thing you want to do is you want to write the quantity to be optimized as a function in terms of one other variable. This function has a name, and it's called the objective function. So if I want to find the maximum volume of something, what I have to be able to do is write the volume as a function of some other variable. Maybe I want to write the volume as a function of radius, or the volume as a function of length, or the volume as a function of the pressure of a gas. Whatever it is, I have to be able to write the volume as a function of something in order to do that. The next thing you have to do is identify the feasible domain of the function. It's not necessarily the mathematical domain. It's that the word problem is going to tell you something about what values are actually possible. And you want to define the domain to be limited to the set of possible values. And the goal, if you can achieve it, you can't always, is to try to get the domain to be a closed and bounded interval. Recall that finding the min and max on a closed and bounded interval had a very nice, tight recipe-like procedure, which is just you find all the critical numbers, you find the endpoints, you evaluate the function at the endpoints, and that gives you the answer. So that's why you want to find that the feasible domain is a closed and bounded interval. Can't always do it, but in the nicest type of problems you can. So then the next thing you do is you just use the calculus optimization procedure to find the minima and maxima. You find the critical numbers. If the domain is closed and bounded, you just plug in the endpoints and the critical numbers. If the domain is not closed and bounded, you may not have a min or a max. So just for example, if I have a domain, if I find the domain is something like A infinity, I might end up in a situation like this, where, as you can see, there's a min, but there's no max. Also might end up in a situation like this, where here again, there's no max, there is a min, there's a local max, but it's not the absolute max. So as you see, intervals like A infinity are not as nice as closed and bounded intervals, but sometimes we have them, and at very least we'll be able to say this problem has an optimal minimal solution, but no optimal maximum solution. So we'll get to those types of problems. So those are some of the harder problems. We'll do those. So I want to start out with a problem that many of you have already seen, but we want to do it in sort of a calculus way. And this is the farmer problem. I know many of you have seen a problem like this. So this comes from pre-calc, but the way that you solved it was probably you just plugged it into a graphing calculator and got the answer. So we're going to see what the calculus solution to this is. So a farmer has 120 feet of fence and wants to build a rectangular pig pen next to a river. And we're going to assume that pigs can't swim, so the farmer doesn't need to use any fence next to the river to keep the pigs from escaping. So what dimensions, length and width, will produce the pen with the largest possible area? So what you want to do here is write out quantity to be optimized, and that is the area of the pen. Now, 2, we want to write the area as an objective function. Actually, I'll just say as a function of another variable. The name of the function is the objective function because that's our objective, is to optimize that function. So here's the thing. So let's draw this situation. Draw the water in blue. Okay, so here's the fenced area. So if I have, let's say, this is going to be a rectangle, so those sides are going to have length x, and we could say that this side has length y, but we actually know more about it because we know that x plus x plus y has to equal 120. So that means that y equals 120 minus 2x. This is actually a very, very important step because we only know how to do optimization in one variable. This is not a multivariable calculus course. If I were to tell you that the area is equal to x times y, you'd have to wait until Math 251 to be able to solve that problem, to be able to say anything about where the mins and maxes are there. So I actually need to get this in terms of a single variable, x. So it's very important that I was able to rewrite y in terms of x, so now I'm only going to have one variable. If you end up in a step where you see something like a is equal to x squared y cubed, and you can't rewrite y in terms of x, you're completely on the wrong track to solve the problem. So just be aware of that. If you have more than one variable on the right side of the equation, then you need to do something else because you're not going to be able to find the answer. Okay, so so what we know now is that the area of the pen as a function of x is going to be x times 120 minus 2x, which equals 120x minus x squared. Okay, so now let's choose the domain. Clearly, this function has all real numbers as its domain because, oh, sorry, 2x squared, correct. Thank you. It's a typo there. Thank you. So clearly this function, it has all real numbers as its domain, but that's not really what we care about because if you think about it, I could put in negative numbers for x, but there's no such thing as a fence of negative length. So x can't be less than 0, because I can't choose I can't choose a length of x that's negative. It's also the case that x can't be more than 60. Why? If you look at the expression for y, 120 minus 2x, if I had a number that was more than 60, then I'd have a negative width of the pen. The most I can do is, if I, in the most extreme case, I go 60 feet in that direction, and then I go 60 feet in that direction, and I leave myself no width. So I can't have either less than 0 or more than 60. So the domain is 0 and 60. Now, we can probably suspect that we're not going to be choosing either 0 or 60, because then the pig would have to be very, very thin in order to fit in the pen. But at the very least, we can say that those are the bounds on either side. And as we know, we want to use a mathematically closed interval, because we're going to be able to get the minimum and maximum area of the pen very easily. So now what we're going to do is we're going to optimize. Sorry, I'm just going to turn the page so that we have more space. We're going to optimize a of x equals 120x minus 2x squared on the interval 0, 60. So what we do is we find a prime of x, because we're going to look for the critical numbers. So that's going to equal 120 minus 4x. We're going to solve a prime of x equals 0, which means that 120 minus 4x equals 0, which means that 120 equals 4x, which means that x equals 30. So 30 is a critical number. And obviously, there are no places where this derivative is undefined. So now we're going to check critical numbers and endpoints. So we calculate a of 0. Recall, you can see up here what the function was. A of x was that. So a of 0 is 120 times 0 minus 2 times 0 squared, which is 0. A of 30, that's the critical number, is 120 times 30 minus 2 times 30 squared, which is 3,600 minus 1,800 equals 1,800. And then a of 60 is 120 times 60 minus 2 times 60 squared, which was 7,200 minus 7,200, or 0. As you expect, if I choose the extreme cases, I just get a pen that has either 0 length or 0 width, so it has an area of 0. What that means is that that's the maximum value. The pen that we want to choose is going to have an x of 30, so 30, 30, and then 120 minus 2x gave us 60. So we want to choose a pen with a width of 30 feet, or sorry, a width of 60 feet and length of 30 feet, or 30 by 60. So there's the answer in calculus. You probably were asked to do in pre-calc was set up this problem and then plug it into a graphing calculator and look for the minimum, or just use the fact that the objective function here is quadratic, so we know that its maximum occurs at the vertex. But this is sort of the calculus way of doing it, which works for functions that are not parabolic, and that's why we use this procedure. Okay, so any questions about this? Okay. By the way, the question that does come up is in the problem presumes that I don't need to fence the water area because pigs can't swim. Is that true? That is correct. That is not true. So, as you see, pigs actually can swim. So, and now you have. And so it turns out that the premise of this entire problem is false. If you don't fence the water, the pigs are just going to escape. It's just that if I made the problem four-sided, then the answer is really boring. The answer is just construct a square. So it could escape anyway. They fly. At least in a Pink Floyd concert, they do. I actually did see the flying pig once in that concert. So. Perhaps we were at the same concert. So, explain step 3, yeah. Okay, so there's a request to explain step 3. So the point is that, I mean, this function, unlike the completely abstract functions that we were doing in section 4.2, it represents something. Since x represents that length, it can't be less than 0. And so that's where we get the x can't be less than 0 part of this from. As far as the 60, for the same reason that x can't be less than 0, y, which represents the width, also can't be less than 0. So in other words, I have to have that y is greater than or equal to 0, just for physical reasons. So that means that since we know that y equals 120 minus 2x, that means that that number has to be greater than or equal to 0. So 120 has to be greater than or equal to 2x, and 60 has to be greater than or equal to x, which I can then flip around and say x is less than or equal to 60. That's where I get those numbers from. Did that answer your question? Okay, good. So, all right, so let's do one more of these, and then we'll do some more of them the next week. So here's one that's a little bit more abstract. Rectangle inscribed in parabola. So let's find the dimensions of the rectangle of maximum area whose base is the x-axis, and that can be inscribed inside the parabola y equals r minus x squared for some positive number r. So here's the picture of what we're doing. So I have this parabola. So this is the parabola y equals r minus x squared. And that's the number r. And what I'm trying to do is I'm trying to draw or to inscribe a rectangle, in the parabola and give it the maximum area that I can. So what I really want to do is, if you think about what this looks like, I'm trying to choose x. So here's like a very skinny rectangle. And if I choose x way out here, I get like sort of a short and wide rectangle. So I'm trying to choose kind of the optimal value of x. I'm going to let x be some number to the right of the x-axis. So it's going to be a positive number because the symmetry of the parabola means that if I choose x here, the parabola really grows in both different directions. So, so what I'm trying to do is choose x somewhere between 0 and that point so that the rectangle has the largest area possible. So let's think about what the dimensions of this are. First of all, what is this point here? We want to find this point. We're looking for the point where y equals 0. So 0 equals r minus x squared gives us x squared equals r, or x equals plus or minus root r. We can obviously see this is on the positive side. So this is going to be the point square root of r 0, and this is going to be the point negative root r 0, like that. So those points are going to be useful in a minute. Here we have the point. This is going to be x comma r minus x squared, because we know it's going to be xy, and I know what the value of y is. So first of all, let's look at the quantity. Quantity to be optimized is the area. So 2, we want to write area as a function something. Well, if x is here, then that means that that's negative x. And that means that this width here is 2x. You can also see from what the y part of this coordinate is that the vertical dimension of the rectangle is r minus x squared. So that means that this is a 2x by r minus x squared rectangle. So the area of x is 2x r minus x squared equals 2rx minus 2x cubed. In different color. So there's the objective function. Let's choose the domain. All right, based on this model, I can't really let x be less than 0. It's like, sure, I could choose x. I could choose x like over there. But if I did, then I'd be describing sort of a flipped around rectangle. So we're going to say that x can't be less than 0. Just answer that question. How did I get r minus x squared? I got it because if you look at the height of the rectangle, we know that the y coordinate of this point is r. The y part of the coordinate is r minus x squared, and down here, the y coordinate is 0. So I'm just subtracting. In other words, the distance, the vertical distance between this point and the bottom of the rectangle has to just be the y part of the coordinate. Because that's the definition of the function. Because it's a point on the parabola. Sorry, I'm just reading the questions. Okay, got it. Okay. So we see that x, because I'm going to choose x so that it's to the right of the x-axis, since the rectangle grows in both directions, I'm going to say that x can't be less than 0, and x can't be more than square root of r, because I can't put x further to the right than that point. So the domain is going to be 0 square root of r. Now 4, we just optimize. Since we know that a of x equals 2rx minus 2x cubed, means that a prime of x equal to 2r minus 6x squared. That gives us 2r equals 6x squared, or x squared equals 2r over 6, where x equals plus or minus, I should write this as r over 3. So x equals plus or minus r over 3, but we're only considering values between 0 and root r. So we're going to choose only square root of r over 3. We're going to discard the negative value. So now I have the critical number. Now that I have the critical number, all I need to do is check endpoints in the critical numbers. So I have 2x, r minus x squared. I'll just take a minute to finish this up. I get a of 0. I already calculated these. You can try them at home. I just want to save a little time. A of 0 was 0. A of the square root of r was also 0, as we expected, because that's just going to be either a rectangle of 0 height or 0 width. A of root r over 3 gives us 2 root r over 3 times r minus, if I take root r over 3 and square it, I just get r over 3. So that equals 2 r over 3. R over 3 minus r minus r over 3 is 2r over 3. So that gives us 4r over 3 square root of r over 3. So clearly this is the rectangle of largest width. The dimensions we want to choose are a rectangle of 2r over 3 by 2r over 3. That's going to be, since I'm going to choose this point here, square root of r over 3. That gives us a rectangle that's 2 square root of r over 3. And then up here, it's going to have, if I plug in everything, I get a vertical distance of 2r over 3. So that's the dimensions of the rectangle. Okay. Anyway, that's it for today. Any questions about this? Oh, just because it goes in both directions, because here I've got 0 and square root of r over 3, but then over here I've got negative root r over 3 as the left boundary. So I have to double the width of the rectangle. I will publish some I will publish some questions for the exam to work on for the exam. What is the purpose of the 4r over 3? That just came out of the mathematics of it. Just plugging in root r over 3 into the area function, I got 4r over 3. Okay. All right. Anyway, that's it. So you're free to go. Anyone have any last questions? I'll stick around for another minute. And otherwise, have a good weekend, everyone. That puts so much pressure on me, James. I'll tell you what, Sam and I will cook something up for inspiration for next week. I'll send you my question of. I will send you my. I'll send you my collection of inspirational poems. No, I've got some good ones. You know, I always work on the correct crescendo. So let's see.